Hi, welcome to SDT University. I am Pallavi Ranjan, Faculty of Engineering and Technology. Today we are going to talk about perceptron network, activation functions, and the problem of linear separability when it comes to perceptron network. Let's go ahead. A perceptron is a neural network unit, that is, an artificial neuron that does certain computations to detect features or business intelligence in the input data. Perceptron was introduced by Frank Rosenblatt in 1957. He proposed a perceptron learning rule based on the original MCP neuron. A perceptron is an algorithm for supervised learning of binary classifiers. This algorithm enables neurons to learn and processes elements in the training set one at a time. Now let us discuss the types of perceptron, that is, single layer and multilayer perceptron. Single layer perceptron can learn only linearly separable patterns, whereas multilayer perceptron or feed-forward neural networks with two or more layers have a greater degree of processing power. The perceptron algorithm learns the weights for the input signals in order to draw a linear decision boundary. This enables you to distinguish between the two linearly separable classes +1 and -1. And also, it is to be noted that supervised learning is a type of machine learning used to learn models from labeled training data. It enables output prediction for future or unseen data. Now let us focus on the perceptron learning rule in the next section. Perceptron learning rule states that the algorithm would automatically learn the optimal weight coefficients. The input features are then multiplied with these weights to determine if a neuron fires or not. The perceptron receives multiple input signals, and if the sum of the input signals exceeds a certain threshold, it either outputs a signal or does not return an output. In the context of supervised learning and classification, this can be then used to predict the class of a sample. Now let us look at the perceptron function. Perceptron is a function that maps its input x, which is multiplied with the learned weight coefficient, and output value fx is generated. Fx is equal to 1 or 0 depending on the values, that is w. If w dot x plus b is greater than 0, then the value comes out as 1, otherwise it is 0. In the equation given above, w is the weight of real valued weights. B is bias, that is, an element that adjusts the boundary away from origin without any dependence on the input value. X is the vector of input x values. Summation I is equal to 1 to m wi xi is where m is the number of inputs to the perceptron. The output can be represented as 1 or 0. It can also be represented as 1 or -1 depending on which activation function is used. Now let us look at the inputs of a perceptron in the next section. A perceptron accepts inputs, moderates them with certain weight values, then applies the transformation function to output the final result. The image here shows a perceptron with a Boolean output. A Boolean output is based on inputs such as salaried, married, age, past credit profile, etc. It has only two values, yes or no, or you can also take it as true or false. The summation function multiplies all the inputs of x by weights w and then adds them up as shown on the screen. Now let us look at the activation functions of a perceptron. The activation function applies a step rule which then converts the numerical output into +1 or -1 to check if the output of the weighting function is greater than 0 or not. For example, if summation Wi xi is greater than 0, then final output O is equal to 1. That is when you can issue the bank loan. Else, final output O is minus 1, which means that you deny the bank loan. Step function gets triggered above a certain value of the neuron output, else it outputs 0. Sine function outputs plus 1 or minus 1 depending on whether neuron output is greater than 0 or not. Sigmoid is the S-curve and outputs a value between 0 and 1. Perceptron with the Boolean output. Inputs are given as x1, x2 up till xn, and outputs are given as O of x1, x2 up till xn, where you can define O of x1 up till xn is equal to 1 or minus 1 depending on whether the sum of weights and bias is greater than 0 or not. Weights Wi is a contribution of input xi to the perceptron output. W0 over here is bias or threshold. If summation of w dot x is greater than 0, output will be plus 1, else it will be equal to minus 1. The neuron gets triggered only when weighted input reaches a certain threshold value. O of x is equal to sine of wx, and sine of y is equal to 1 or minus 1 depending on y is greater than 0 or not. An output of plus 1 specifies that the neuron is triggered, whereas output of minus 1 specifies that the neuron did not get triggered. SGN over here stands for sine function with output plus 1 or minus 1. Now let us look at what is the error in perceptron model. In the perceptron learning rule, the predicted output is compared with the non-output. If it does not match, the error is propagated backward to allow weight adjustment to happen. A decision function phi z of perceptron is defined like this to take a linear combination of x and w vectors. The value z in the decision function is given by w1 x1 plus w2 x2 until it reaches wm xm. The decision function is plus 1 if z is greater than threshold theta, and otherwise it is minus 1. This is what we call as perceptron algorithm. Now let us look at the bias unit. For simplicity, the threshold theta can be brought to the left and represented as w0 x0, where w0 is equal to minus theta and x0 is equal to 1. The value w0 is called the bias unit. Phi z is equal to 1 if z is greater than equal to 0, otherwise it is minus 1. The figure shows how the decision function squashes wtx to either plus 1 or minus 1 and how it can be used to discriminate between the two linearly separable classes. Perceptron has the following characteristics. Perceptron is an algorithm for supervised learning of single-layer binary linear classifier. Optimal weight coefficients are automatically learned. Weights are multiplied with the input features and decision is made if the neuron is fired or not. Activation function applies a step rule to check if the output of the weighting function is greater than 0. Linear decision boundary is drawn enabling the distinction between the two linearly separable classes plus 1 and minus 1. If the sum of the input signals exceed a certain threshold, it outputs a signal, otherwise there is no output. Types of activation functions include sine, step, and sigmoid functions, which we will be discussing later on. Now let us look at how we can implement logic gates with the perceptron model. The perceptron learning rule converges if the two classes can be separated by the linear hyperplane. However, if the classes cannot be separated perfectly by a linear classifier, it could give rise to errors. As discussed in the previous topic, the classifier boundary for a binary output in a perceptron is represented by the equation shown as w dot x is equal to 0. The diagram here shows the decision surface represented by a two-input perceptron. In figure A, examples can be clearly separated into positive and negative values. Hence, they are linearly separable. This can include logic gates like AND, OR, NOR, and NAND. In figure B, it shows examples that are not linearly separable, as in the XOR gate. Diagram A is a set of training examples and the decision surface of a perceptron that classifies them correctly, whereas diagram B is a set of training examples that are not linearly separable, that is, they cannot be correctly classified by any straight line. X1 and X2 here are the perceptron inputs. Now let us talk about the logic gates. Logic gates are the building blocks of a digital system, especially neural networks. In short, they are the electronic circuits that help in addition, choice, negation, and combination to perform complex circuits. Using the logic gates, neural networks can learn on their own without you having to manually code the logic. Most logic gates have two inputs and one output. Each terminal has one of the two binary conditions, low or high, 0 or 1, represented by different voltage levels. The logic state of a terminal changes based on how the circuit processes the data. Based on this logic, logic gates can be categorized into 7 types. That is AND, OR, NOT, NAND, NOR, XOR, and XNOR. The logic gates can be implemented with perceptron are discussed here. For AND gate, if two inputs are true, that is +1, the output of perceptron is positive, which amounts to true. Whereas in OR gate, if either of the two inputs are true, the output of the perceptron is positive, which amounts to true. Both AND and OR gates are linearly separable as shown in the graph. Let us discuss the XOR gate now. XOR gate, also called as exclusive OR gate, has two inputs and one output. The gate returns a true as the output if and only if one of the input states is true. This is the truth table for an XOR gate. Unlike the AND and OR gate, the XOR gate requires an intermediate hidden layer for preliminary transformation in order to achieve the logic of an XOR gate. An XOR gate assigns weights so that the XOR conditions are met. It cannot be implemented with a single layer perceptron and it requires multi-layer perceptron or MLP. H over here represents the hidden layer which allows XOR implementation. I1, I2, H3, H4, O5 are 0, that is false, or 1, that is true. T3 is the threshold for H3 and T4 is the threshold for H4. T5 is the threshold for O5. H3 will be equal to sigmoid of I1 cross W13 plus I2 cross W23 minus T3. So this is the activation function. We are using binary sigmoid for the XOR gate. Whereas H4 over here will be the binary sigmoid, that is the activation function of I1 cross W14 plus I2 cross W24 minus T4. O5, which is the final neuron in the output layer, will be the activation function, that is binary sigmoid function for H3 cross W35 plus H4 cross W45 minus T5. So today we covered perceptron network, that is single layer and multi-layer perceptron, activation functions, linear as well as non-linear. Also we looked at the problem of linear separability, which is also called as the XOR trouble when it comes to perceptron. In next lecture, we are going to talk about Hope field networks. Till then, keep learning, keep growing. See you next time.